The first electricity systems were direct current. It worked, but there was a problem. DC didn't transmit easy. Thus arose a new technology built around alternating current, AC. The two sides clashed briefly, but the winner was clear. AC won. 60 years later, however, a subsea power link to an island in Sweden transmitted a new message. DC was back. In today's video, the rise, fall, and re-rise of DC power transmission. Let us begin with Thomas Edison and the first practical incandescent light bulb, which debuted in December 1879. The arrival of the light bulb lit up electricity demand across both Europe and the United States. You might say that the light bulb was the AI data center of its era. To power these light bulbs, Edison set up these central stations. These central stations would be in the heart of the city, generating electricity, which is then carried to consumers via underground wires. Edison trial ran the idea in London at the Holborn Viaduct Power Station. He then built America's first commercial central station on Pearl Street in Manhattan's financial district. It started operations in 1882. The electric central station idea was borrowed from the gas industry's gas holders, large containers in urban areas for storing gas. Edison saw the gas lighting industry as the main competitor for his light bulbs. Central stations also accommodated a major technical limitation of his electrical lighting system. Pearl Street can only economically serve customers within half a mile. Imagine electricity transmission as like water going through a pipe. This is not a new metaphor. People use it all the time. The current in the wire can be likened to the flow of water in the pipe, though I should note that this common metaphor is not completely accurate. Wires do not transport electrons like pipes transport water. Anyway, the water pressure pushing that water through the pipe is your voltage. Voltage is the force, measured in volts, that drives electrical energy through wires. As the current travels through a material, even a conductive metal like copper, it suffers losses. Vibing electrons collide with atoms, releasing heat energy. This heat energy causes losses. If we want to avoid suffering too much energy loss, we can either have a thicker copper wire at lower voltage or a thinner copper wire at higher voltage. The problem with option A is that copper is expensive, and Edison's company had to install miles of cable just for Pearl Street. More copper can make that prohibitive. The problem with option B is that Edison did not have a technology that can raise or, quote, step up the voltage of the DC current. Edison later invented a three-wire modification to option A that extended low-voltage DC's transmission range from half a mile to about a mile. Even so, this did not change the fact that Pearl Street DC system only made financial sense in dense cities. But what if we are not using direct current? Alternating current is constantly switching direction, the flow of the current reversing course some number of times every second. This also creates a changing magnetic field. Now, if you pass that changing AC current through the first of two copper wires coiled around an iron core, its changing magnetic field will induce voltage in that second copper coil. DC does not flip, so its magnetic field is unchanging, just like my love for you guys, and thus it induces no voltage from the iron core and coiled copper setup. This interesting effect was first discovered by the electromagnetic luminary Michael Faraday back in 1831, but nobody did much with it for half a century. Then, in 1883, a Frenchman named Lucien Goller and his English partner John Dixon Gibbs demonstrated at the Royal Aquarium in London a power distribution system using what Goller called secondary generators. These secondary generators are like the setup that I mentioned earlier, two sets of copper coils wrapping around an iron core. The thing would later be given the name transformer, a name proposed by Edouard Hospitalier. The transformer makes it possible to step up an AC current's voltage for transmission. Upon arrival, we again use transformers to step down the voltage. The following year, Golar and Gibbs demonstrate their system by transmitting electricity at 2,000 or 3,000 volts, the sources are not clear which, some 40 kilometers from the Italian city of Turin to Lanzo. The news hailed the technology as capable of bringing power to various people in the rural areas, which the Edison system cannot do. People soon recognized that with AC, they didn't have to build many small, inefficient central stations in the city. Pearl Street was a tiny operation squeezed between two buildings. Rather, people now can build a huge, more efficient power station outside a city and use AC to transmit it to the people. Several engineers tried to overcome DC's long-distance limits, particularly in Europe. One such pioneer was a French civil engineer named Marcel Duprez. Over the span of 10 years, between 1876 and 1886, he experimented with long-distance DC transmission. In 1882, he worked with the German industrialist Oskar von Miller to design a 2,000-volt DC-powered transmission line. It started at a generator in a mine in Maybach, Germany, a town in Bavaria at the foothills of the Alps, and went to the Glass Palace in Munich, where it powered an artificial waterfall, pumping German beer, I wish. Unfortunately, the line suffered low efficiencies of just about 25% and broke down after a few days. By then, AC power transmission was rapidly gaining popularity in both the United States and Europe. In the United States, AC and DC clashed in the battle of the currents. It was not much of a battle, to be honest, mostly the creation of a frenzied media. Golar and Gibbs' demonstrations convinced George Westinghouse to buy the American rights for the system. George then assigns his chief engineer, William Stanley Jr., to fix some practical issues with the design. One such issue with the Golar-Gibbs transformers was that they were connected in such a way as to make them unstable. So if you had connected to them a series of lamps, then adding or subtracting one lamp affected them all. Stanley remedies this interference issue. It's not clear whether he improved the system or created a brand new one, but what he did enabled Westinghouse Electric's founding in 1886. At first, the two companies stuck to their niches, Edison and DC in the urban areas, and Westinghouse and AC in the rural and small town areas. AC technology had an advantage in long-distance transmission, but lacked practical meters and efficient motors. Then in 1888, several new inventions tipped the scale. Westinghouse licenses Nikola Tesla's patent for an AC induction motor, and the rotary converter makes it possible to turn AC power into DC power for existing motors, railways, and so on. Facing daunting economics, Edison runs a PR campaign to paint AC as dangerous. At the same time, he lobbies for legislative voltage caps to blunt AC's economic advantages in long-distance transmission. But this doesn't last long. In 1889, Edison's financiers consolidate most of his companies into one company called Edison General Electric. Edison's operational control wanes, and the company starts edging towards AC. Then, in 1892, Edison General merges with the AC-centric Thomson-Houston Electric Company to create the General Electric Company we all know and love. Let's jump over to Europe. The publicity surrounding the 1884 Turin-Lanzo AC line lead to various cities in Britain, France, and Italy adopting the Golar-Gibbs transmission system. But those Golar-Gibbs systems were replaced within a few years. In 1885, a famed Hungarian team of engineers at the electric and railway company Ganz & Company, nicknamed the ZBD team, produced a more practical transformer. Like Stanley's transformers, the Ganz transformers fixed several practical issues with the Golar-Gibbs. Moreover, the GaN's company had the resources to back its adoption. GaN's transformers quickly became widespread. Golar and Gibbs had no chance, and their factory shut down in 1887. Early DC pioneers like Oscar von Miller switched over to AC as the technology's economic advantages became clear. In 1891, von Miller built a 176-kilometer AC line between the cities of Frankfurt and Laufen, settling the debate between AC and DC long-distance transmission. For Golar, this was hard to take. To add insult to injury, he was denied a patent for his technology while others were not, leading to several fruitless legal battles. The resulting pain and financial ruin sent the man to madness and an early grave. Research continued on to find something to challenge AC's advantages in long-distance transmission. The most clever solution was one brought forth by the Swiss engineer René Thury. Dubbed the King of DC, he pioneered what was called the Thury system. The system steps the voltage up or down using a series of connected generators and motors. To step up, Thury connected several DC generators in a line, allowing them to cumulatively stack voltages for transmission. Upon arrival at the other end of the line, Thury has lined up a bunch of motors, and together they split the voltage amongst themselves as a step down. Many Thury systems were built in England, Hungary, Russia, France, and Switzerland. They were particularly well suited for hydroelectric plants because the generators broke down if they spun too fast. Waterfalls were good enough for this, though fast-spinning thermal plants, not so much. Thury systems had a reputation for reliability issues, but a few remained in operation long after AC won the day, one hanging on all the way until 1936. In the end, though, even that system was replaced by an AC system. So AC long-distance transmission won, but it was not a complete victory. There is a limit to how far you can transmit high-voltage AC power via underground or subsea cable. The major reason for this is capacitance. Capacitance refers to an object storing charge, and they happen whenever you have two conductors between an insulator. Well, inside the cable, you have conducting copper wrapped in an insulator and a conducting metal sheath. That makes it a big capacitor. An AC current's voltage flips 50 or 60 times every second, so the current is constantly charging and emptying the capacitor 50 to 60 times each second. This wastes energy and generates heat. The longer the cable, the bigger the capacitor, and the more heat it generates. At about 50 to 100 kilometers, most of your AC current is being used to charge a useless battery inside your cable. At this point, you either need to go with overhead lines, which are more spread out and have fewer claddings, or go DC. With DC, you no longer have the flipping, so the cable/capacitor only charges once, and that is it. Another major benefit concerns how AC power networks have different frequencies. It is an infamous Reddit tidbit that Japan's eastern power grid runs on 50 Hz, while its western power grid runs on 60 Hz. So power generated in one half can't be transmitted to the other half without causing instability. Direct current has no frequency, so if we can convert high voltage AC to DC, then we can send it between those grids. It was not until the 1920s when a device finally emerged to make high voltage DC transmission technically feasible. That device is the Mercury arc rectifier, or valve. Rectifier basically means it turns AC into DC. Valve means valve. I shall use the terms interchangeably. Invented in 1902 by the famous Peter Cooper Hewitt, the first Mercury arc rectifiers were a glass tube vaguely reminiscent of a Wobbuffet. Inside the tube, there is a pool of heated liquid mercury that serves as a cathode, which means that mercury pool emits electrons, which creates an arc that moves a current from cathode to anode. This only happens when the AC current is at its positive voltage half cycle. When the AC current flips to negative voltage, the opposite direction, anode to cathode, is blocked because the anode cannot normally emit electrons. Ergo, the rectifier is a one-way valve that only lets the current through when it is in its positive half cycle. Hewitt himself recognized that a high-voltage version of his rectifier can convert a high-voltage AC current into a high-voltage DC one, thus making long-distance DC transmission feasible. To handle these larger currents and higher voltages, Mercury arc rectifiers had to get physically larger, but it became apparent early on that glass envelopes were too fragile to scale up. So as early as 1905, engineers started trying to make rectifiers out of metal tanks like iron or steel. It required some tricky engineering, but when completed, worked better, though performance remained temperamental, often subject to changing temperatures and cleanliness. The Mercury arc rectifier did have one more major problem: reverse arcs, or arcbacks. This is when the one-way valve unexpectedly reverses, especially at higher voltages or lower currents. It took some time to understand why this was happening, not exactly like we can look at it. When the AC current is in its negative voltage phase, the metallic anode might get bombarded with positive mercury ions. With enough bombardment, the anode starts emitting electrons. That is what the cathode is supposed to be doing, not the anode. With enough electrons, the anode emits an arc during the negative voltage phase. Current can suddenly now pass uncontrollably in either direction. Arcbacks can cause short circuits in the larger system, and over time they also damage the seals around the anode, causing leakage and permanent damage to the rectifier. This problem bedeviled engineers for years and cannot be solved simply by moving the cathode and anode further apart, because the positive mercury ions form a sheath near the anode during the negative AC phase. So, negative voltage concentrates there, inducing the bombardments to happen. For many years, this arcback problem limited mercury arc rectifiers to only a few kilowatts, well below what was needed to send electricity. Then in 1929, a researcher named Uno Lamm set himself on the task of arcbacks. Born in 1904 in Sweden, he studied electrical engineering at the Swedish Royal Institute of Technology. After his military service, he joined ASEA, which was one of Sweden's most famous electric companies. ASEA would later merge with a Swiss company called Brown Boveri to create today's ABB. In 1929, Lamm was asked if he wanted to join a project to develop a high-voltage mercury arc rectifier with no arcback. He would work on it for the next 40 years. He never managed to get rid of them entirely, but he did reduce it. As I mentioned, a key reason why arcbacks happen was because the mercury ion sheath near the anode concentrates a lot of negative voltage, thus inducing bombardments and the emitted electrons. Lamm's idea to prevent this concentration was to insert electrodes between the cathode and anode to quote-unquote pull mercury ions away from the anode. ASEA patented this concept in the late 1930s. It did work, and during the 1940s, Sweden's State Power Board, their state utility, considered using HVDC to transmit power from the Harsprånget hydroelectric power plant from the north of Sweden to the south. But the technology was then not ready, and they ended up using traditional AC technology. It was not until 1944 that Lamm's team and ASEA had themselves a commercially viable high-voltage rectifier capable of handling some 60 kilovolts for HVDC. By the way, Sweden was not the only country interested in HVDC. The Germans were too. Nazi Germany started researching high-voltage direct current transmission in the lead-up to the war. the justification apparently being that underground power cables are harder to bomb than overhead AC ones. The Nazi government invested massive resources to build high-voltage rectifiers and inverters. They dual-tracked two types of rectifiers, one Mercury arc and another called the high-pressure air blast arc converter. It used a puff of air to blow out the arc and cut the line. In German, they call it the Lichtbogen-Stromrichter, which is an awesome name. But sadly, it suffered massive, insurmountable technical problems, so Mercury arc rectifiers prevailed. Near the war's end, an HVDC line of uncertain specs was built to transmit power from a power plant on the Elbe River near the city of Dessau to a Berlin suburb some 70 miles away. The power would then be sent to the Berlin grid. The Elbe project, as it was called, was completed but never put into service because Germany was collapsing at the time. The Soviets captured this technology and sent it back to Russia as war booty. It was used to produce an HVDC line between Moscow and the city of Kashira in 1950. After World War II, Sweden's electricity demand grew very quickly, which meant rapidly expanding electricity transmission capacity. In 1945, Sweden's State Power Board and ASEA built a 50-kilometer test HVDC line between a station at Trollhättan and Mellerud in Sweden. This seemed to have good results, so in 1950 the board officially ordered an HVDC power transmission link for the island of Gotland on the Baltic Sea. The island used to have its own thermal plant, but high fuel costs led them to try this instead. Lamm himself led the $4.5 million project. It involved first building a converter station in the town of Västervik on the mainland, where high-voltage Mercury arc rectifiers convert HVAC power into HVDC. That then feeds into the subsea cable, which was a pretty standard cable. It's about 50 millimeters wide, ran about 98 kilometers long at an average depth of about 121 meters, and operated at about 100 kilovolts and 20 megawatts. The cable surfaced near the island's only town of Visby. It then goes to another plant to be converted into AC power for local grid distribution. Attention had to be paid to ensure that the power conversion matched the local AC grid's frequency. The Gotland HVDC power link went live in 1954. It attracted attention from other countries like Japan and the United Kingdom. The latter commissioned ASEA to build the first cross-channel HVDC link, completed in 1961. During the Mercury arc valve era, which spanned about 15 years, ASEA built and delivered 11 HVDC projects all over the world in New Zealand, Japan, North America, and Europe. Uno Lamm went on to work on nuclear energy technology, but in 1965 he moved to San Francisco to lead an HVDC project there. ASEA had entered into a collaboration with General Electric to build the Pacific Intertie. The Intertie is an HVDC link that today brings power from the dams of Oregon to the households of Southern California. As part of this collaboration, the two swapped technologies. General Electric licensed ASEA's Mercury arc valve-based HVDC tech. ASEA got, in turn, access to a revolutionary solid-state technology, the thyristor. The thyristor, or silicon-controlled rectifier, entered the market in 1957. It's a solid-state semiconductor device made up of 4 layers of alternating P and N-type silicon material. They're like transistors in that they switch things on and off, it's just that they switch a power current. Being solid-state devices, thyristors are not only sturdier than Mercury arc valves, but also more reliable. They do not suffer arcbacks. It conducts in a forward direction. You can use them to build smaller and more power-efficient AC-DC converters. Thyristors rapidly replaced Mercury arc valves. HVDC was one of the valve's last strongholds. The first air-cooled thyristor was installed in Gotland in 1967. When it showed to have worked well, the Swedish State Power Board ordered a full conversion. Thyristors were used for 25 years in HVDC projects before being replaced by another solid-state power semiconductor called the insulated gate bipolar transistor, or IGBT. Improving technologies like the IGBT have pushed forward the limits of what we can do with HVDC. Gotland was a 100 kilovolt project and about 100 kilometers long. But over the years, the voltages have gotten higher and lengths longer. In 1985, ASCA's successor, ABB, delivered the first phase of the massive HVDC Itaipu project, an overhead line with 3.1 gigawatts and 600 kilovolts. It stretches 785 kilometers between the Itaipu Dam to the megacity of Sao Paulo. It's one of Brazil's most important HVDC schemes and remained the largest project until 2010 when China finished the Xiangjiaba Dam HVDC link. Brazil has since come back with a yet larger scheme. The reality, of course, with all this battle of the current stuff, is that AC and DC are not enemies. It makes little sense to root for one over the other. They're both technologies, tools to be used for certain situations. For decades, we had nothing other than AC for long-distance transmission. DC's 30-year return to the stage is a welcome addition to the toolset. Alright everyone, that's it for tonight. Thanks for watching. Subscribe to the channel, sign up for the Patreon, and I'll see you guys next time.